Hi, I'm Grace Fanson, and I'm a third-year PhD student at MIT. Today, I'll be sharing my research quantifying the effects of impact cratering on Martian valley network preservation. On Mars, we use the term valley networks to describe branching systems of valleys that resemble terrestrial drainage networks. These features are some of the best evidence we have for past surface water flow. In case you haven't heard, the Mars of today is very cold and dry. It can't support liquid water for durations long enough to carve something as extensive as valley networks. So these features alone tease a totally different era on Mars, one with stable liquid water and a climate to support it. The valley-forming era ended in the first quarter of Mars's geological history. In the 3.5 billion years since, these globally distributed features have been exposed to their environments. In particular, they have been exposed to billions of impact events. On the left, you can see the spatial distribution of valley networks, and on the right, you can see the spatial distribution of impact craters. You can probably guess where this is headed, especially because it's written on the slide, but we hypothesize that the global record of valleys is incomplete due to destruction by impact events. This hypothesis is motivated by several observations. We have seen evidence for the removal of valley networks. For example, this is CTX imagery of Warrego Vallis. Valley networks are traced in blue and impact craters are traced in black. You can see the labeled impact crater has stamped out a portion of the valley network. Another motivating observation is a disparity between the spatial abundance of flood canyons and their total eroded volume. For context, flood canyons are formed when crater lakes fill with water to the point of catastrophic overflow. The water spilling from the crater carves deep channels. These channels account for almost a quarter of the eroded volume on Mars, even though they only represent 3% of valley length. Could this just be a survivorship bias, where smaller valley networks are more vulnerable to destruction? Or could flood canyons be a dominant form of fluvial erosion on Mars? Improving constraints on valley network preservation will improve our understanding of Mars's early water inventory and the climatic conditions in which they formed. To approach this hypothesis, we created a model to simulate the effects of 3.5 billion years of impacts on Mars. We track which valleys are preserved after bombardment, record how a valley's preservation depends on depth, reconstruct the pre-impact distribution of valley depths on Mars, and finally estimate the water required to carve the valleys. Now let's dive into the model. On Mars and other planetary bodies, we can use the abundance of craters on the surface to constrain the surface's age. If a surface has been around for a comparatively long time, it will have experienced more impact events than a relatively younger surface. We can also use this relationship in reverse. If we generally know the age of a feature, we can figure out how many impacts it must have accumulated. In this plot on the x-axis, we have time, where the left side is 4 billion years ago, and the right side is today. On the y-axis, we have the total number of craters a feature would have accumulated since that time. The blue lines represent craters of different sizes, with darker colors corresponding to bigger craters. We know the valley formation era ended approximately 3.5 billion years ago, so we draw a line there and use the abundances of each crater size in our model. Now that we have the abundance of impact craters for our model, we need rules for what it means for a valley to be destroyed. The relative size of a valley and the crater matters. If we have a small impact in a large valley, it's not going to make a huge difference, but a large impact on a small valley will completely erase it from the record. To compare the depths of valleys and impact craters, we need to normalize the topography. For our model, we used Kohala, Hawaii to represent Mars at the end of the valley-forming era because it has a wide variety of valley sizes that covers the range of Martian valley depths. But we don't really care about the overall elevation, like we see here, with blue being high elevation and white being low elevation. Instead, we use a tool called progressive black top hat to flatten out the topography, so we are essentially looking at a flat plane with valleys carved into it. The colors now correspond to valley depth as it relates to the banks of the valley. Now we can make a simple comparison between the depth of an impact crater and the depth of the valleys. Okay, now we have impact rates and a way to compare the sizes of the features. Here's a zoomed-in, simplified explanation of how the model works. This panel represents a valley depth map, with -3 being the deepest part of the valley and -1 being the shallowest part. Enter our impact crater. Here we have deep values in red and orange, and the depositional ejecta blanket in yellow and green. The model will compare the depth of each pixel. If the crater bowl is deeper than the valley is deep, we consider it destroyed. If the ejecta blanket is able to bury the valley, we consider it destroyed. And in the intermediate case where the ejecta blanket doesn't totally bury the valley, it partially fills it in, making it shallower and more susceptible to destruction by future impactors. Okay, now that you know what the model does, let's look at the qualitative results in full scale. On the left, we have topography prior to impact, and on the right, we have topography after impact. Valley depths are shown in blue. You may notice that the large canyons are almost completely preserved, while the smaller valleys are significantly reduced. Now we want to quantify this level of destruction. The way we did this is by counting up the abundance of each depth and tracking how many of them survive impacting. Of the original -1 depths, none of them survive in this example, while 80% of the deepest portions do survive. Applying this to our model, we find this preservation curve. We can treat this like a probability. If a valley is 150 meters deep, it is very likely to survive, while anything shallower than that is more vulnerable to destruction. Now let's bring this back to Mars. This is our measured distribution of valley depths on Mars. Note the log scale on X and Y axes. And this is the same preservation plot from the last slide, just with a log scale on the x-axis. We can apply the corresponding preservation rate for each valley depth bin to calculate the original abundance at that size. This is the adjusted frequency distribution of valley depths on Mars based on our preservation measurements from the model. Note that this is a conservative estimate. In our model, we only account for impact craters, though there are many other erosional forces that could erase valley networks. Our model suggests that at least 7% of valley network volume has been erased by impact craters alone. Now, to estimate the amount of water that carved the volume of the valley networks, we follow the work of Rosenberg et al. 2019. VVN is the volume of the valley network, lambda is the rock porosity, and Vs is the sediment volume. In other words, this equation is the entire eroded volume of the valley networks on Mars minus all the empty space equals the sediment volume, which can be calculated with the new eroded volume we derived from our model and reasonable estimates for rock porosity. Now, this volume of sediment was carried away by some amount of flowing water, Vf. The ratio between those volumes is equivalent to the ratio of the sediment flux and fluid flux, which we constrain using observations from Earth. Rearranging this equation, we can solve for the fluid volume, which is what we're after. Our result suggests an increase in water volume of around 7%. We hypothesize that the global record of valley networks is incomplete due to destruction from impact events. Over the course of this project, we found that preservation is depth-dependent, with valleys deeper than 150 meters surviving, while shallower valleys are increasingly susceptible to destruction. Our model suggests that impact craters have erased at least 7% of valley network volume. This value is not large enough to account for the relative ubiquity of flood canyons, but is significant enough to improve constraints on the total water that flowed across ancient Mars. I want to say a big thanks to my collaborators on this project, my wonderful advisor, Gaia Stuckey-DeQuay, and Alex Morgan from PSI, and of course the wonderful Gaia Lab as a whole. I also want to thank the mentors and communities who have helped me find my path in this field. I'd like to note that DEI efforts have played an important role in making this science possible, and I'm proud to pay it forward by leading mentorship programs in my department at MIT. Thanks so much for listening.